So for number 10, we're just going to rewrite these using logical connectives, right? And now we just have to remember the order of operations and then rewrite everything. So for number 10a, we'll begin with that one. We have if f has a relative minimum, right? So if, this means that we're going to have like p implies q, right? Where p is our f has a relative minimum. So I'm going to put f has relative minimum if this and f is differentiable, right? At x naught, and so we're going to change this, and f is differentiable at x naught, and then f prime of x naught is equal to 0. So we have to put a parenthesis here and say then. So then this arrow for our conditional, f prime of x naught is equal to 0. And now let's see if f has a relative minimum and f is differentiable at x naught, then f, yeah, that is correct. And maybe because these are complicated statements, we could just put an additional set of parentheses so that we can evaluate each one separately, right? And then this one, yeah. Okay, so for b, we're going to have if n is prime, then n equals 2 or n is odd. So once more, we have a conditional, right? We have if n is prime, then, and also we have the or, the disjunction, n equals 2 or n is odd. So we have for b, we have n is prime if n is prime, right? So I'm going to put parentheses here, then, so our conditional arrow, then n equals 2 or n is odd. So I'm going to put the parenthesis here, and I'm going to say n equals 2 or n is odd, right? And let's see, because or goes before the conditional, I'll just put an added set of parentheses here just so that we can evaluate these first. Okay, so that's all good for item B. Now let's look at item C. So item C is, we have a lot of stuff going on, right? We have a number is real and not rational whenever x is irrational. Now the whenever part, it's important. Let's just remember that if we have P implies Q, this is equivalent to saying Q whenever P, right? Whenever P. So what this really means is that our P is x is irrational and our Q is this whole thing. So we're going to just, and let me just highlight this Q, right? Q, and then I'm going to put P, just so that we can color code it. All right, so we'll begin with saying P, if P, then Q, because we do have a conditional, right? So for item C, we're going to say that x is irrational. If x is irrational, then Q, right? So irrational, and then arrow. Now, let's look at whatever Q is. So a number x is real and not rational. So we have conjunction. So x is real, right? And not rational. And not rational. So for this one, we just have to put some parentheses. Now remember that not comes first, right? So we're going to put an added set of parentheses here, not. And then we're going to put a set of parentheses, let's see, around x is real, right? Because then we're saying, first we applied not, then we have to apply x is real and do the conjunction. So here, just so that we look at the order of operations, right? So for D, let's see, x is irrational if x is real and not rational. Okay, cool. So for D, we have if x equals 1 or x is equal to -1, then absolute value of x is equal to 1. So we do have a conditional, right? So we'll open our parentheses because we have x equals 1, and then or. So or, disjunction, x is equal to -1, right? Then, and I'm just going to open the parentheses once more, absolute value of x is equal to 1. All right, now all that's missing is for us to put our parentheses to indicate the order of operations. So we'll just put another parenthesis around each of these statements just so that it's super clear that we're evaluating the or first. Yep, that is it. Let's do item E. So for item E, we do have a biconditional, right? Because we have an if and only if. So our P is f has a critical point at x naught. So this one is straightforward. F has critical point at x naught. And then if and only if, so our double arrow, if and only if f prime of x naught is 0 or f prime of x naught does not exist, right? So we do have a disjunction within this statement. So we're going to say f prime of x naught is equal to 0 or our disjunction, f prime at x naught does not exist. So now we just have to put an added set of parentheses within this disjunction just to show that we're applying the or first, right? That is our order of operations. So we'll put these just so we can see that we're doing the or first. All right, we did E. Now let's do F, right? S is compound if and only if S is closed and bounded. So once more, we do have a biconditional, right? So F here, biconditional, and we're going to say S is compact is our P. So S is compact if and only if, so double arrow, right? And now we have S is closed and bounded. So we have a conjunction here. So S is closed, and S is bounded. Now, once more, we do have to put parentheses to indicate order of operations because and is evaluated before the biconditional, and S is bounded. So that was it for our F. Is a necessary and sufficient condition, okay? So for our G, let me just zoom out so we have enough space. So for our G, B is invertible is a necessary and sufficient condition. So whenever we do have the necessary and sufficient, it's a different way of saying if and only if, right? Because we say that P is a sufficient condition for Q and Q is necessary for P. So for G, we're saying B is invertible. And once more, necessary and sufficient condition means if and only if the determinant of B does not equal 0, right? Does not equal 0. So this one's pretty straightforward. It's just about the interpretation of the necessary and sufficient condition. Now we go for item H, right? Once more, I'll zoom out a little bit. So for item H, what do we have? We have 6 is greater than or equal to n minus 3 only if n is greater than 4 or n is greater than 10. Now, let's think about what this only if means, right? P only if Q. Is that what it means? So let's think about it. We're going to draw here our... why is this not drawing? Okay. This is our Q and this is our P, right? So we can think of it as a subset. So we can say P only if Q. I'm only in P only if I'm in Q, right? if I'm not in P, then, sorry, if I'm not in Q, then I can't be in P. So P only if Q. Therefore, we have that P if Q, right? So here, 6 greater than or equal to n minus 3, only if means conditional, P if Q. So if n is greater than 4 or n is greater than 10, n is greater than 4, or is represented by the disjunction, n is greater than 10. And once more, we do have to put parentheses because the or goes first, right? All right, so all we're missing now is item I, J, and K. So for item I, we have that X is Cauchy implies, I don't know if you say Cauchy or Cauchy, implies that X is convergent. So we have to think of it again. What does it mean? Implies. We have P implies Q, right? P implies Q, so P implies Q is the same thing as saying if P, then Q. So we have a conditional statement. So let us set this up as a conditional statement. So for I, we have here that P is X is Cauchy. X is, this is our P. If P, then Q, right? So I have a conditional when X is convergent. And we don't need any more parentheses, I believe. Yeah. Now let's do J. For J, we're saying f is continuous at x naught whenever the limit of x as it approaches, the limit of f of x as x approaches x naught is f of x naught. So once more, P implies Q means that Q whenever P, right? These are equivalent statements. So we're saying, if you look at this diagram, we're saying that if I have P, then I have Q, right? So Q whenever P. Whenever I have P, I'm going to have Q. So just to make it super clear, P implies Q is the same thing as Q whenever P. So actually our P is this guy over here, and our Q is F is continuous. So what we're going to say here is that, so we have a conditional statement where lim of F of X equals F of X naught as X approaches X naught implies that F is continuous at X naught. Yeah. So that is, I'm running out of space. I'm going to leave it this way, and that is it for our translating our statements, right? And I'm just going to kind of zoom out for you guys to see everything, and that is what we have.